Good morning. Today we are working on Lesson 2 of Unit 6 called Truth and Equations. And I just wanted to go over the learning targets before we begin. So the first one is I can replace a variable in an equation with a number that makes the equation true and know that this number is called a solution to the equation. And the second one, I can match equations to real-life situations they could represent. All right, let's get started. So we're going to use equations to represent real-life stories and see what it means to solve an equation, because we've heard that expression a lot. And up till now, we usually have used it to mean let's find the answer to a calculation, but we're getting a little bit into algebra now. And when we talk about solving an equation in algebra, we're usually talking about an equation that contains a variable, and we solve the equation by figuring out what number or numbers that variable must be equal to in order to make the equation true. So let's look at our warm-up. 2, 1, called 3 letters. So the first statement, the equation A plus B equals C could be true or false. So now they're giving us some values of A, B, and C and asking us, is the equation true or false? If A equals 3, B is 4, and C is 5, is the equation true or false? So what we need to do is substitute those numbers, 3, 4, and 5, into the equation and see if we get a true statement. So let's see, if A is 3, I better select a pencil here. So if A is 3, and that's not what I wanted. Let's try this again. If A is 3 and B is 4 and C is 5, is this a true statement? Is 3 plus 4 equals 5? No, it's not. On the left side, 3 plus 4 equals 7, and on the right side is 5, and they are definitely not equal. So this equation would be false. Then it asks us to find new values of A, B, and C that could make the equation true. So what I need are two values that when I combine them equal the third value. So you could come up with an infinite number of solutions. In fact, we could keep A and B equal to 3 and 4, and then we would know that C would have to be the combination of 3 and 4, which is 7. So we could say, all right, we're still going to let A equal 3, B equal 4, and C equals 7. And now we do have a true statement. 3 plus 4 does equal 7. Part C asks us to find new values of A, B, and C that make the equation false. So, and again, you could pick, in this case, you could probably randomly choose any 3 values for A, B, and C, and the likelihood is that they're going to make the equation false. So let's, I'll say, let's let A equal 6, and B equal 7, and C equal 8. And we know this is false because 6 plus 7 does not equal 8. And you could have come up, like I said, there's an infinite number of combinations that would make this equation false. All right, let's move on to the next part. Now we have the equation x times y equals z could be true or false. So instead of an addition equation, we have one involving multiplication. If x equals 3, y is 4, and z is 12, is the equation true or false? So again, if we substitute those numbers into the equation x times y equals z, will we get a true statement or a false statement? So Let's try this. I'm going to type this time because my writing is so terrible on here. So if x equals 3 and y is 4 and z is 12, we substitute those numbers in for the 8, x times y equals z. Is the equation true or false? And we can pretty clearly see, we know our math facts, this is true. Now, part B says find new values of x, y, and z that make the equation true. So we just need to find two numbers that when we multiply them together equal the third number. So we can pick, again, there's an infinite number of solutions to this. We could pick any two numbers in our math facts. Let's use 5 and 8. So if x equals 5 and y equals 8, and we know these two multiplied together equal 40, so z would equal 40. And this also, these values of x, y, and z also make the equation true. In part C, find new values of x, y, and z that make the equation false. So we could just pick any numbers that we know when we multiply them together do not equal the third number. So let's pick, and again, infinite number of solutions here. How about 9 times 4, which I know that equals 36. So I can pick any value of z that is not 36 and have this be false. So let's just pick 17. Okay. All right, so that is our warm-up. Okay. So let's move on to activity 2 called story time. It says here are 3 situations and 6 equations. Which equation best represents each situation? If you get stuck, draw a diagram. So again, this is always what I believe is the most challenging part of mathematics. Is it's not actually doing the calculations, it's being able to use math as a tool to represent and solve real life situations. So let's look at the first one. After Elena ran 5 miles on Friday, she had run a total of 20 miles for the week. She ran X miles before Friday. So she runs 5 miles on Friday. Before Friday, she ran X miles, and altogether she runs 20 miles. So I think she ran 5 miles on Friday, and before Friday she had run X number of miles, and the total of the two is 20. So which equation best represents each situation? And I can see it's almost exactly as I've written it. Down here, x plus 5 equals 20 is the same as 5 plus x equals 20. So that's the one that's going to match that. Let's look on to number 2. Andre's school has 20 clubs, which is 5 times as many as his cousin's school. His cousin's school has X clubs. This is one of those where you can translate it into a mathematical expression almost literally from the verbal. Andre's school has 20 clubs, so he has 20, and that is, so that's our equal, 5 times as many as his cousin's school, and his cousin's school has X clubs. And this is a perfect illustration of why we move away from using an X to represent multiplication, because if I use it, I get 5xx, and that's sort of confusing. So again, this is why we move to either using the dot as a symbol for multiplication, or just using juxtaposition, which is where we just put the number right next to the variable and know that the multiplication is implied. So actually I could just write this as 5x, 20 equals 5x. And when I do that, if I come down and look at my available equations to choose from, I notice this one right here, 5x equals 20, is the same as 20 equals 5x. So this, oops, I guess I'm going to move back to my this one would be the solution to this phrase. Okay, our last one. Jada volunteers at the animal shelter. She divided 5 cups of cat food equally to feed 20 cats. Each cat received X cups of food. Well, this is sort of a tricky one because if I wrote this, I would say, well, she took 5 cups of cat food and she divided it equally among 20 cats, and the amount of food each cat got would be X. So I would do 5 divided by 20 equals X. But I see that's not one of my options in my solution. So it's been written a different way. So I have to think 5 divided by 20 equals X, and we kind of worked on this before. I could think of this as, let's see. If we remember from our unit on fraction division, one way I could look at this is also that X times 20 equals 5. So 20 times X equals 5. And when I rewrite it that way, I recognize that it is this equation. And I think that's a tricky one, kind of because of the way the problem's written. All right, let's move on to the next activity. Oops. All right, now we are moving on to activity 2-3, using structure to find solutions. Here are some equations that contain a variable and a list of values. Think about what each equation means and find a solution in the list of values. If you get stuck, draw a diagram. Be prepared to explain why your solution is correct. So, we're not moving right into solving equations by using an algorithm just now. Right now we want to look at these equations and think about what they mean and see if we can figure out how to find a solution that way. So the first one, number 1, 1,000 minus A equals 400. So thinking about what this means, I have 1,000. And I want to know what would I have to remove from that 1,000 to get 400? What would A have to be? Well, on this one, you can kind of do intuitively. I know that if I have 1,000 of something and I end up with 400 of them, then I've lost 600 of them. So just by inspection, I know that 1,000 minus 600 equals 400. So when I go down to my list of solutions here, I want to see, is 600 one of my possible answers? Yeah, it is. Okay, that one didn't seem too terrible. Let's look at this next one. 10e equals 1. This means 10 times something equals 1. What would I need 10 of to make 1 whole? This one might be a little trickier to think about, but if I think back to my fraction division, I know if I have 10 times something equals 1, then 1 divided by that 10 equals the something. I know I would, and I can also think about the idea of a reciprocal. I know that a number times its reciprocal always equals 1. So if I have 10, the reciprocal of 10 is 1/10. So 10 times 1/10 equals 1. So in this case, my E would have to be 1/10. So I'm going to come down here and see, is that a possibility? And it's not written as a fraction, but if I look right here, there's 1/10, right? 0.1. So that's my solution. Okay, let's move on to number 3. 12.6 equals b plus 4.1. So I know these two numbers combined, b, whatever that is, and 4.1 must equal 12.6. So I know that if I do 12.6 minus the 4.1, that should give me whatever b is. So 12.6 minus 4.1. 6 minus 1 is 5. Decimal moves straight down. And 12 minus 4 is 8. So my solution should be 8.5. And there it is. Okay. Let's move back up. 4. H plus 3/7 equals 1. So 1 minus 3/7 must equal h if h and 3/7 combined equals 1. So I have to think about 1 minus 3/7. So I want to change 1 into 7/7 because if we're doing fraction subtraction, they have to have the same denominator. And 7/7 minus 3/7 is 4/7. So h must equal 4/7. So let's go down. And there it is. Good. All right. Number 5, 8 times c equals 8. Let's this one think about it. What times 8 equals 8? Well, it must be 1, right? Because 8 times 1 equals 8. So c must equal 1. Let's see if that's down here. Yep, right there. How about number 10? Number 6. 10 equals 0.5 times f. So if you think about it, 0.5 is 1/2. So 1/2 times some number equals 10. Well, 1/2 of what number is 10? So if we think about it that way, 1/2 times what equals 10? So most of us just intuitively know that 1/2 of 20 is equal to 10. So I think that f is going to be 20. Let's go down and look at this. Is it 20? Yeah, there we go. All right, number 7. 2/3 times some number equals 10/9. 2/3 times d equals 10/9. So this one's a little tricky to think about. Sometimes it helps if you think of an analogy with whole numbers, because I think just when students see fractions, it automatically kind of muddies the problem. So think of it if this was this problem. If I had 4 times some number equals 12, how would I solve that mathematically? Well, I would know just on inspection that d must equal 3 because 4 times 3 equals 12. So if I was thinking how would I solve that mathematically, I would have said, well, 12 divided by 4 equals 3. So 12 divided by 4 equals d. So now come back to the original problem. It's really the structure is no different. So if I want to figure out what d is using this analogy, I would do 10/9 divided by 2/3 must equal d. And if I do that, 10/9 divided by 2/3, and for fractions division, I keep change flip, so it would be 10/9. I gotta lower this a little bit. 10/9 times 3/2, And that's going to give me, I should simplify, but just because I'm running out of room here, 30/18. I could divide the top and bottom by 6. 30 divided by 6 is 5. 18 divided by 6 is 3. So I get that D is equal to 5/3 or 1 2/3. Let's see if it's down here. Oh, there it is, 5/3. Okay. And now our last one. 99 hundredths is equal to 1 minus G. So 1 minus some number must equal 99 hundredths. So what would I have to subtract from 1 to get 99 hundredths? So intuitively, I think it's going to be 1/100th. If I take 1 and subtract 1/100th, I'm left with 99 hundredths. And there would be my answer. All right, so that was subtracting. I didn't feel the need to draw a diagram for any of these. I could kind of reason them out in my just using kind of some logic. But if you are doing these types of problems and you're stuck, drawing a diagram is good. And I also think sometimes using an analogy involving whole numbers to help you see what strategy you would use to solve it if it had whole number solution, coefficients and stuff, makes it a little bit easier. All right, are you ready for more? One solution to the equation A plus B plus C equals 10 is A equals 2, B equals 5, and C equals 3, which makes sense. Those three numbers total equal 10. How many different whole number solutions are there to the equation A plus B plus C equals 10? Explain or show your reasoning. Well, there's not an infinite number of solutions, because they do put a restriction on here that the solutions have to be whole numbers. So we wouldn't be able to use fractions, decimals, or negative numbers. If that was the case, you could come up with an infinite number of solutions. But in this case, because they are whole number solutions, they would have to be positive whole numbers, and since the sum has to be less than 10, all of those numbers would have to be less than 10. So there is a restriction. And this actually gets into a branch of mathematics called combinatorics, permutations and combinatorics, and you could use what's called a tree diagram to help you solve it. Because I could start like this. I could say, oh, this is so bad. If A equals 0 and B equals 0, then C would have to equal 10. And if A equaled 0 and B equaled 1, then C could equal 9. And if A equaled 0, B could equal 2, and then C would equal 8. And you could go down the list for this. And then you would have to do the same thing all over again. If A equaled 1, B equaled 0, C equaled 9. You could kind of, would really take more room than we have here and more time. So maybe we will do this later if we have time. All right, and then we come to the summary. So an equation can be true or false. An example of a true equation is 7 plus 1 equals 4 times 2. So for an equation to be true, the value on the left side of the equal sign has to be equal to the value on the right side of the equal sign. So an example of a false equation is 7 plus 1 equals 9. On the left side, the value is 8. On the right side, the value is 9, so it's false. An equation can have a letter in it. For example, u plus 1 equals 8. This equation is false if u equals 3 because 3 plus 1 does not equal 8. This equation is true if u is 7 because 7 plus 1 is equal to 8. A letter in an equation is called a variable. In u plus 1 equals 8, the variable is u. A number that can be used in place of the variable that makes the equation true is called a solution to the equation. In u plus 1 equals 8, the solution is 7 because 7 plus 1 equals 8. When a number is written next to a variable, the number and the variable are being multiplied. For example, 7x equals 21 means the same thing as 7 times x equals 21. A number written next to a variable is called a coefficient. If no coefficient is written, the coefficient is 1. For example, in the equation p plus 3 equals 5, the coefficient of p is 1. All right. That's it for the notes. You can go ahead and get started on your homework.